Welcome to Learning Outcome 3, all about how a reaction at equilibrium responds when we disturb it. We'll build up Le Chatelier's principle and use it to predict what happens when we change the conditions on a reversible reaction. In this outcome, you'll describe what dynamic equilibrium really means in a closed system and state Le Chatelier's principle precisely. Then you'll predict the effect of changing concentration, pressure, and temperature, explain why a catalyst never shifts the position of equilibrium, and pull it all together by applying it to the industrial Haber process. Let's start with reversible reactions. Plenty of reactions can go both forwards and backwards, and we show that with a double half arrow, meaning the reaction is reversible. Take nitrogen plus hydrogen, which is in equilibrium with ammonia. The reactants form products, while at the same time, the products reform the reactants, both happening together in the vessel, and neither direction ever fully stops. So what exactly is dynamic equilibrium? It's only reached in a closed system, where nothing can enter or leave. At that point, the forward and backward rates become equal, so the concentrations of reactants and products stay constant. But the reaction hasn't stopped. It's still busily going both ways. That's the meaning of the two words, dynamic, because there's constant activity at the molecular level, and equilibrium, because there's no net change in the amounts. A few definitions to nail down. A closed system is one where no matter can enter or leave the vessel. Dynamic equilibrium is the state where the forward and backward rates are equal and concentrations stay constant. The position of equilibrium describes the relative amounts of reactants and products present, and a reversible reaction is one that can go both ways, shown by that double half arrow. It helps to contrast dynamic equilibrium with static equilibrium. Static equilibrium is when nothing is happening at all. The process has genuinely stopped, like a book resting on a table with no molecular activity. Dynamic equilibrium, our chemical kind, is quite different. The forward and backward reactions carry on continuously. Their rates are equal, so there's no net change, and the molecules are constantly interconverting even though the concentrations hold steady. Now, the key principle, named after the French chemist Henri Le Chatelier. It says that if you impose a change on a system at equilibrium, the position of equilibrium shifts in the direction that opposes that change. In other words, the system acts to partly counteract whatever disturbance you've made. That single idea lets us predict which way an equilibrium will move, and it applies to changes in concentration, pressure, and temperature. Here's how to apply it in practice. First, identify the change you've imposed on the system. Then ask which direction would oppose that change. If the equilibrium shifts to the right, more product forms. If it shifts to the left, more reactant reforms. Remember, the system never completely cancels the change. It only reduces it. And your reasoning should always be guided by the state symbols and the moles of gas on each side. Let's take concentration first. If you increase a reactant, the equilibrium shifts right to remove the excess. Increase a product, and it shifts left to remove that. Going the other way, if you decrease a reactant, it shifts left to replace it, and decrease a product, and it shifts right to replace that. In every case, the system opposes the change in concentration, which is why continually removing a product keeps driving a reaction forwards. Let's reason one through. For the reaction of ethanoic acid with ethanol, which is in equilibrium with the ester ethylethanoate and water, what happens if we add more ethanol? Ethanol is a reactant on the left, and we've raised its concentration. So by Le Chatelier, the system shifts to oppose that increase. That means the equilibrium moves to the right, using up the added ethanol and forming more ester and water. Here's a slightly different case. In the decomposition of calcium carbonate, which is in equilibrium with calcium oxide and carbon dioxide, what happens if we keep removing the carbon dioxide gas? The carbon dioxide is a product on the right, and taking it away lowers the concentration of product, so the system shifts to replace it. The equilibrium moves to the right, meaning more calcium carbonate keeps decomposing, and the reaction is effectively driven towards completion. Pressure is next, and it only matters when gases are involved. The trick is to compare the total moles of gas on each side of the equation. Increase the pressure, and the equilibrium shifts towards the side with fewer moles of gas. Decrease it, and it shifts towards the side with more. If the two sides have equal moles of gas, then changing the pressure has no effect at all. And remember, solids and liquids don't count in this. Let's try the Haber reaction. Nitrogen plus hydrogen in equilibrium with ammonia, and raise the total pressure. On the left we have 1 mole of nitrogen plus 3 of hydrogen, so 4 moles of gas. On the right we have just 2 moles of ammonia. Increasing the pressure favors the side with fewer gas moles, and 2 is fewer than 4, so the equilibrium shifts to the right, increasing the yield of ammonia. Now a case where pressure does nothing. For hydrogen plus iodine in equilibrium with hydrogen iodide, what happens if we raise the pressure? The left side has 1 mole of hydrogen plus 1 of iodine, so 2 moles of gas, and the right side has 2 moles of hydrogen iodide as well. The moles of gas are equal on both sides, so there's no side with fewer moles to favor, and increasing the pressure has no effect on this equilibrium. Temperature is the subtle one, because its effect depends on the sign of delta H. The forward and backward reactions always have opposite signs, so if one direction is exothermic, the other is endothermic. Raising the temperature favors the endothermic direction, while lowering it favors the exothermic direction. The system is again opposing the change, this time in thermal energy. And temperature is special. It's the only condition that actually changes the value of the equilibrium constant, Kc. Let's split this by the sign of delta H. If the forward reaction is exothermic, so delta H is negative, then raising the temperature shifts the equilibrium left and lowers the product yield, while cooling shifts it right for more product. As in the Haber reaction, with a delta H of minus 92 kilojoules per mole. If instead the forward reaction is endothermic, delta H positive, it's reversed. Heating shifts it right for more product, and cooling shifts it left, as with dinitrogen tetroxide in equilibrium with nitrogen dioxide at plus 57 kilojoules per mole. Let's reason one out. For sulfur dioxide plus oxygen in equilibrium with sulfur trioxide, delta H is minus 197 kilojoules per mole. So what happens if we raise the temperature? The forward reaction is exothermic, since delta H is negative, which makes the backward reaction endothermic. Raising the temperature favors the endothermic direction, and that's the backward, left-hand direction here. So the equilibrium shifts left, and the yield of sulfur trioxide falls as the temperature rises. Here's a nice visual one. Dinitrogen tetroxide, which is colorless, is in equilibrium with nitrogen dioxide, which is brown, and delta H is plus 57 kilojoules per mole. What happens to the color when we heat it? The forward reaction is endothermic, since delta H is positive, and raising the temperature favors the endothermic direction, so the equilibrium shifts right to form more nitrogen dioxide. With more brown gas present, the mixture goes a deeper brown color. What about a catalyst? A catalyst speeds up the forward and backward reactions equally by lowering the activation energy for both directions. That means equilibrium is reached faster than it would be otherwise, but, and this is the key point, the position of equilibrium is not changed at all. The equilibrium yield stays exactly the same. A catalyst affects only the rate, never the position. Let's reason that through with the Haber process, which uses an ion catalyst. Does it raise the equilibrium yield of ammonia? The catalyst lowers the activation energy for both directions, so the forward and backward rates both increase by the same factor, and equilibrium is reached more quickly. But the balance point between those two rates is completely unchanged. So the answer is no. The catalyst doesn't change the yield, it just helps the system get to equilibrium faster. Let's collect some terms. A catalyst speeds a reaction up by lowering the activation energy without being used up. Exothermic means a reaction that releases heat, with delta H negative, while endothermic means one that absorbs heat, with delta H positive. And compromise conditions are conditions chosen to balance yield, rate, and cost together rather than maximizing any single one of them, which brings us neatly to the Haber process. The Haber process makes ammonia for fertilizers from nitrogen plus hydrogen in equilibrium with ammonia. The forward reaction is exothermic, with delta H of minus 92 kilojoules per mole, and the left side has 4 moles of gas against just 2 on the right. So high pressure favors the product side, with its fewer gas moles, and a low temperature favors the exothermic forward reaction. An ion catalyst is added to help the system reach equilibrium quickly. But there's a tension over temperature. For the highest yield, you'd want a low temperature, since the forward reaction is exothermic. The trouble is that at a low temperature, the reaction is painfully slow, and a wonderful yield that takes forever to appear is no use industrially. Push the temperature up, and you get a fast rate but a poor yield. So a middle value is chosen, around 450 degrees Celsius, balancing an acceptable yield against a workable rate. Pressure has a similar tug-of-war. High pressure shifts the equilibrium to the right for more ammonia, and it usefully raises the rate too. But very high pressure demands strong, expensive equipment and carries a greater safety risk. So in practice, a pressure of about 200 atmospheres is chosen, which balances a good yield against the cost of the plant and keeping it safe. Let's lay the compromise out plainly. What the theory alone would want is a low temperature and a very high pressure for maximum yield. But that completely ignores rate and cost and would be impractical for real industry. What's actually used is about 450 degrees Celsius, giving a reasonable yield fast enough to be useful, and about 200 atmospheres, giving a good yield with an affordable plant, plus an ion catalyst to reach equilibrium sooner. Any unreacted nitrogen and hydrogen are simply recycled. Let's reason through the classic question: why isn't the Haber process run at a very low temperature, when that would boost the equilibrium yield? It's true that because the forward reaction is exothermic, a low temperature raises the yield, but a low temperature also gives a very slow rate, so the ammonia would form far too slowly to be economic. That's why about 450 degrees Celsius is used, a compromise that produces a useful amount of ammonia at an acceptable rate. Let's pause for some questions. Can you state Le Chatelier's principle in your own words? At dynamic equilibrium in a closed system, what two things are true? For the Haber reaction, which way does the equilibrium shift when pressure is increased, and why? And why does adding a catalyst not change the equilibrium yield? Have a think. A few more to test yourself. For sulfur dioxide plus oxygen in equilibrium with sulfur trioxide, with delta H of minus 197 kilojoules per mole. What happens to the yield of sulfur trioxide when the temperature rises? Can you give a reaction where changing the pressure has no effect and explain why? Why is the Haber process run at about 200 atmospheres rather than something much higher? And why do we call 450 degrees Celsius a compromised temperature?